Hey class, Mr. Angie here. For today's lesson, we're going to be taking a look at section 15.4, which is going to deal with segment relationships in circles. Now, for today's lesson, we have one learning goal, and our learning goal for today is that you will be able to find segment lengths using the segment relationships in circles. So we're going to talk about three different segment relationships in circles today. We're going to talk about the chord product theorem, the secant product theorem, and then we're going to end with the secant tangent product theorem. So we're going to talk about those three different theorems today, and then we have three examples that highlight and allow us to practice using those theorems. So with that said, the first theorem on deck is the chord product theorem. Now, we have talked about chords before in section 15.1, and a chord is just a line segment that's in a circle that has both endpoints on the circle. So, two examples of a chord would be AB, because it's a line that goes through the circle, and its endpoints A and B are both on the edge of the circle. Same with CD. This is another chord because both endpoints are on the circle, endpoints C and D, and it goes through the circle. So we have our two chords, AB and CD. The chord product theorem states, if two chords intersect in a circle, so they both intersect at point E, then the product of the lengths of the segments of the chord are equal. So, when these two lines intersect at point E, it breaks the two chords up into four different parts. The chord product theorem states that the products of the lengths of the segments of the chords are equal to each other. That means the two segments for the chord AB, which is AE and EB, if I multiply the value of these two segments together, it equals the value of these two segments multiplied together. So the chords are broken into two parts, so we have four parts overall. The two parts for each chord, if I multiply them, so the blue times the green equals the red times the purple. So that is the chord product theorem. That the segments of the chords, you can multiply their values together and they equal the other chords segments multiplied together. So what we're going to use this today in example 1 is they will tell us the measure of three of the different segments, and you have to find a missing segment. So you would do like 3 times x equals 4 times 5. Per se. So the product of the length of the segments of each chord are equal. So that means this times this equals this times this. And that is that. So we are going to use the chord product theorem to help us answer our questions for example 1. In example 1 is going to ask us to find the value of x and each chord length. And we're going to use the chord product theorem to help us do that today. So if we look at example 1, part A, so they tell me that CE is 6, EB is 3, ED is 2, and they want us to go through and find the value of x, which is going to tell us the value of AE. So, using the chord product theorem right here, what the chord product theorem tells us is that this segment times this segment equals this segment times this segment. So if I set that all up, it is going to be x times 3 equals 6 times 2. So you're going to multiply the two segments from each chord set it equal to the two segments multiplied for the other chord. So we have x times 3 equals 6 times 2. So all we have to do is just go through and solve for this problem. So x times 3 is 3x, and 6 times 2 is going to give us 12. So if we go through and solve for this problem, 12 divided by 3 is going to give us x to equal 4. So I now know that x equals 4. So that finds the value of x. And then the follow-up question wants us to find or tell what the different chord lengths are. So to figure out the chord lengths, you're just going to add the two segments from each chord. So if we look at the chord AB, that is this whole segment here. I know this part is 4 and this part is 3. So the whole thing of AB is 7. And then if I carry that idea for CD, if this part is 6 and this part is 2, then the whole thing of CD is 8. And that is our answer for part A. So example 1, using the chord-chord product theorem, this part times this part equals this part times this part. Go through, multiply, then divide, and that's going to tell you what your missing segment is, and that allows you to go through and find the value of the chords. Now, if we take a look at part B, so for part B, they tell us that KG is 6, HG is 9, IG is X, so that's what we want to figure out, and that GJ is 8. So we need to figure out the length of IG right here, and that is our goal for this problem. So using the chord-chord product theorem, to set this up, it's going to be 6 times x equals 9 times 8. So I'm taking the two parts, the two segments of the chords, multiplying them together and setting them equal to each other. So 6 times x is going to give us a 6x. 9 times 8 is going to give us 72. So if I have 6x equals 72, to solve for x, we just have to do 72 divided by 6. And that is going to tell us that x equals 12. So now that I know that x equals 12, that is my value of x. That tells me my missing segment. You can then go through and find the length of the chords by just adding the two segments together. So what that means is that IK is 6 plus 12. So I know IK to be 18. And then for HJ, it's the two segments of 9 and 8. So if we do 9 plus 8, we get 17 for the length of chord HJ. And that is our answer for part B. Now, C is the same idea as parts A and B. Slight little difference here. So they tell us that AE is 3, BE is 14. They don't tell us what ED is, but they want us to figure out the length of EC. Now, they tell us that the chord AD is 12 units. So that means this whole chord right here is 12 units long. So if I know this whole thing is 12 units long, I know that AE is 3. To figure out ED, it's just 12 minus 3. and 12 minus 3 is going to tell me that ED is 9. So now that I know ED, I know 3 of the segments, and I want to find the 4th segment. So then it's just like parts A and B. So we just set it up as x times 14 equals 3 times 9. X times 14 is 14x. 3 times 9 is going to give me 27. And if we divide by 14, we get x to be 1.93. That is our value of x and our missing segment. Now, in terms of the chord, okay, we already know what AD is. For BC, you would just take 14 plus 1.93, which just gives you 15.93. So, that is example 1 on using the chord-chord product theorem, where they are going to tell you the value of 3 of the different segments of the chords. They want you to find the 4th and final segment of one of the chords, and you're going to use the chord-chord product theorem, where you multiply both segments of each chord and set them equal to each other, as they are the same measure. Alright, so that is example 1 in the chord-chord product theorem. The next thing we are going to take a look at is the secant product theorem. But what we need to talk about first is what a secant is. So I'm going to cover up real quick so we can just focus on secants. Alright, a secant is any line that intersects a circle at exactly 2 points. A secant segment is part of a secant line with at least 1 point on the circle. A secant segment that lies on the exterior of the circle with 1 point on the circle is an exterior secant segment. So we see all of that drawn here. The secant product theorem states this, that if 2 secants intersect in the exterior of a circle, so the secant here would be AE and CE, and they're going to intersect at point E. So these 2 lines, the blue and the purple, intersect at point E. Then the product of the lengths of one secant segment and its external segment equals the product of the lengths of the other secant segment and its external segment. So the secant is AE and its external segment is BE. Whenever they talk about an external segment, it's outside of the circle. So the secant product theorem states that I can take this whole measure of the secant, multiply it to its external part, and that is equal to the measure of the other secant times its external part. So it's going to be blue times red equals purple times green. Secant times external equals secant times external. So we're going to apply that idea for example 2 to go through and find the value of x and each secant. All right, so example 2, we are going to use that secant product theorem. So find the value of x and each secant segment is our directions. If we look at part A, so we have our secant AC and our secant AE, and then our external parts of AB and AD. Now, the goal is to figure out the value of x. So, remember, it is the entire secant segment, so that would be AC, so it's this whole thing, 5 plus x times its external part, which is 5, equals the secant, the other secant, which is AE, so that's 6 and 6, so that's 12, times its external part, which is 6. So it's the whole thing times its external part. The whole thing times its external part. So when you're trying to figure out the whole thing, the whole secant, you have to add the two parts together, the external and the part inside the circle. So that's where this 5 plus x comes from, because it's both these parts added together. 12 comes from 6 plus 6. All right, so our goal is to go through and solve for x, so this is just using our algebra skills. We're going to go through and distribute the 5 to both parts. So 5 times 5 is 25. 5 times x is 5x. And then over here we have 12 times 6, and 12 times 6 is going to give us 72. All right, so we have 25 plus 5x equals 72. So what we're going to do next is go through and just solve like normal for x. So first step is to subtract the 25 to the 72. So if we do 72 minus 25, we get 5x to equal 47. And then to solve for x, we're just going to divide 5 over to the 47. So 47 divided by 5 gives us 9.4. And that is the value of x for part A. Now, it does talk about what is the value of each secant segment. So the secant segment is going to be the whole entire segment. So if we look at AC, that's this whole part, which is 5 plus x. Well, we know x to be 9.4. So it's 5 plus 9.4. So that tells us that AC is 14.4. And then AE is this whole segment, so 6 plus 6, which tells us 12. And that is our answer for example 2, part A, and how you are going to go through and do parts A, B, C, and D. So if we take a look real quick here at part B, okay, we're going to follow the similar idea. So it's the secant times the external part. So the secant is the whole thing. So the whole thing of PS is 8 plus 6. So that's going to be 14 times its external part, which is 6. That equals this other secant, which is this whole thing here of UP, and that is x plus 7 times its external part, which is 7. So again, it's the secant, the whole segment, the 8 plus 6, which gives us the 14, times its external part, which is 6. Equals the secant, the whole thing, so this x plus 7, because it's the value of x plus the value of 7 is the whole thing, times the value of its external part, which is 7. So now that we have 14 times 6 equals x plus 7 times 7, you just go through and solve like we did for part A. So you're going to distribute the 7 to both parts, and then we're going to multiply these two numbers together. So 14 times 6 gives us 84. And if we do 7 times x, we get 7x. 7 times 7 is going to be 49. So we have 84 equals 7x plus 49. All you have to do is just go through, subtract the 49 to the 84, which gives us 35, equals 7x, divide by 7, and that tells us that x equals 5. So now that you know what x equals, that tells us that this part here for ut is 5. So then you can go through and tell what the secants are. SP is 8 plus 6. UP is 5 plus 7. So that tells us that SP is 14 and that UP is 12. And that is how you go through and answer your questions for example 2 in using that secant product theorem. Now, parts C and D are much of the same thing as A and B. I'm not going to run through them in full detail just because it's repetitive and it's just the same thing as A and B, but I will help you set them up. So if we look at C, we're going to take the secant, which is the whole thing, so the 5 plus 5.4, which is going to give us 10.4 times its external, which is 5, equals the other secant, which is 4 plus x, times the external part, which is 4. So that is how you set that part up. You're going to go through and distribute this 4 to the 4 in x, multiply these together, and go through and solve for x. I will leave that for you to do if you want practice on solving this fully out. For D, again, it's the secant, so the entire thing. So that's going to be 4 plus 6, so that's 10, times the external part, which is 6, equals the secant, the other one, and that's going to be x plus 5, times the external part, which is just 5. Now, this one may seem intimidating at first, but if you just set it up, so if we do 10 times 6, we get 60. Combine like terms real quick, so we get a 2x plus 5 times by 5. So you just have to distribute that 5, so it's 2x times 5, 5 times 5, and then you can just go through and solve for x from there. So I will leave parts C and D for you to finish on your own if you would like. They are done in my completed notes if you would like them or to be able to reference them. So that is example 2 on using the secant product theorem. So the last thing that we need to take a look at today is the secant tangent product theorem, and then take a look at example 3. So let's move that on up. All right. So a similar theorem applies when both a secant segment and a tangent segment are drawn to a circle from the same exterior point. A tangent segment is the segment of a tangent line with exactly one endpoint on the circle. Okay, remember in 15.3 we talked about, or 15.2, sorry, we talked about tangent lines. Okay, and tangent lines are lines that are outside of the circle but intersect the circle at one point. So the tangent segment is just going to be a part of that tangent line, just a small part. Okay, so that would be like AB here, or CD here, or CD here. That would be the tangent segment. The secant is the whole other segment, BD, AC, AC. So the secant tangent product theorem states that if a secant and a tangent intersect in the exterior of a circle, so they intersect at C, intersect at B, intersect at C, then the product of the lengths of the secant segment and its external segment equals the length of the tangent segment squared. So what that means is we're going to take the measure of the whole secant segment times its external part, so it's the red times the blue, equals the tangent segment squared. So you're going to do the secant times its external equals the tangent squared. So red times blue equals purple squared. So using that theorem, we're going to apply that in example 3 to find the value of x and the secant segments. All right, so for part A, AB is going to be considered our tangent segment. BC is our external part, and then BD is the secant segment. So if I go through and apply this, it's the secant segment, so that would be BD, so the whole thing of 2 plus x times the external part, which is 2. So this starts very similar to example 2, and then it equals the tangent segment squared. So it's going to be 5 squared. So we then have 2 plus x times 2 equals 5 squared. So all we have to do is just go through and solve for x. So if we distribute the 2 to both parts, we get 4 plus 2x equals 25. So to solve from there, we subtract the 4, which tells us that 2x equals 21. And if we divide by 2, we get x to equal 10.5. So that is the value of x. When it talks about what is the secant segment, well, that's the whole thing of BD. I know that x is 10.5 now. So the whole thing is 2 plus 10.5. So that tells me that BD is 12.5. And that is our answer for part A. So the last one for B, if we set this up again, remember it's the secant, which is the whole thing. So that would be the 6 plus 4. So that's 10 times its external part, which is 4, equals the tangent segment squared. So that's going to be x squared. Again, the secant, so the whole thing, so the 6 plus 4, that gives us 10, times its external part, which is 4, so we have 10 times 4, equals the tangent segment squared, which is x. So 10 times 4 is 40, that equals x squared. So we have 40 equals x squared. So if we go through and solve, we end up with the square root of 40 for the value of x. Now, you could go through and get a decimal for that, and that would work just fine. Also, we could simplify the square root to 2 times the square root of 10. And that tells us the value of x. And if we're talking about the secant segment, well, we already knew what it was because this was 6 and 4. So the whole thing of AC is 10. We just went through and figured out the tangent length. All right, so with that said, that is it for example 3 on using the secant tangent product theorem. So through today's lesson, we have talked about that chord product theorem back in example 1, where the two chords intersect and it forms 4 different segments. You multiply the 2 parts of each chord and set them equal to each other. Then we talked about the secant product theorem in example 2, where you take the length of the secant times its external part, set it equal to the secant or the other secant and its external part. And then we finished with example 3 and talking about the secant tangent product theorem, where you take the secant times its external part and set it equal to the tangent segment squared. So, with that said, that is it for today on section 15.4, segment relationships in circles. And that is it for our video today. So, thank you guys for listening. I hope this was helpful, and I hope you have a good understanding of what to do. And I hope this gives you some good examples to reference as you work on your homework for today. So, with that said, as usual, if you have any questions or need any help, whether over the notes or over the homework, just let me know the next time you see me or send me an email, and I'll be more than happy to help or clarify or give you some guidance however I can. Otherwise, that is it for today. Thank you guys for listening. Have a great rest of your day, and I'll talk to you guys later. All right, bye.